Okay, let's look at another example with projectile motion. In this question, a cannon is fired off a tower that is 80 meters tall at an angle of 30 degrees above the horizontal at a velocity of 54 meters per second. So with projectile motion questions, the first step is always to do your little sketch. Now this sketch doesn't have to be anything fancy, but this is a sketch to symbolize all your variables and to establish a visual representation of what the question's asking. So in this case, the cannon is fired. We don't need to draw the cannon. That you can if you want, but it's not necessary. What the important parts are the initial velocity, so 54 meters per second. It's 54 meters per second. It's the initial velocity at an angle. I'm going to use different colors here to keep this straight. So the angle above the horizontal is 30 degrees. And the height of the tower, that's 80 meters. So we know 80 meters is the height. I'm going to draw that just like this. Okay, so when the object is fired, it's going to follow some kind of trajectory. Here, let me do a kind of a more straight curve here. So it's going to follow some kind of trajectory like this until it hits the ground. And one more important thing with problems like this is splitting up our vector into the x component. So this is velocity in the x direction, and also the y component. And again, I'm going to use different colors for these just to keep them straight. And this is our Vy. And as you'll know, hopefully from your lessons, that Vy, I'm going to put a 1 here because this is just the initial velocity in the y direction. So when it's fired, it has a certain velocity in the y direction, and that is equal to 54 sine 30. So it's the magnitude times the sine of the angle. And the reason that is if you see this vector here, if we move it over here, we get a right angle triangle. Right? We have this right angle triangle, so here we have a right angle. This is a triangle, and we can use SOHCAHTOA. So the sine of 30, according to SOHCAHTOA, the sine of the angle is the opposite over the hypotenuse. So the opposite over the hypotenuse. So if we want to know what this opposite side is, so since sine theta is equal to the opposite over the hypotenuse, and we want to know what is this opposite, what is the value for this, all we got to do is bring this h to the other side. So h sine theta is equal to that opposite side. And that's where we get this formula, h, the hypotenuse, and sine theta, thetas are 30 degrees. And then it's going to be the same thing with our Vx, but with the adjacent. So the Vx is our adjacent side, and it's equal to the magnitude times the cosine of the angle. So it's going to always be this. This is something you're going to see with every single question. As long as you have velocity and an angle, you're going to need to split it up. Split up your vector into its components. Let me move this back. You're going to need to split the vector up into its components, and it's always going to be sine theta, sine of the angle for your y, and cosine of the angle for your x. So now that we've got the first step, which is to just visualize what the question's asking, we can start with part A. How far away will the cannonball land? So we're looking to find this distance. I'm going to find this distance, and I'm going to call it delta dy, because this is distance in the y direction. And it equals, well, we don't know. We don't know what the value is. So here's what we're going to find. And I'm going to write out the steps here in red. So we have a formula for displacement, and that is displacement is equal to the velocity, just in meters per second, multiplied by the time. So something will go a certain speed, say 10 meters per second, and it does that for 10 seconds. Well, when we multiply them together, we'd know that the displacement is 100 meters. So velocity multiplied by time is the displacement. So let's continue on with this formula. Let's see. And in this case specifically, we're looking for, I realized a mistake here. This is actually our dx. This is the x-axis. This up here, our y-axis is like this. So here's our x and y. So in this case, our delta dx is equal to the velocity in the x direction times time. So Vx, we know the value of Vx. I'm going to color code this. Times time. And let's bring this down one step further. So Vx, we know from earlier. We know the value of Vx, so I'm going to plug this in now. So 54 cos 30 times time. And we can actually plug this into our calculator, and I encourage you to follow along with me. It's equal to 46.77 meters per second times time. So we have a speed. It was 46.77 meters per second, and we want to know how many seconds it travels that for. So what is t? What is t? How can we find t? Since it's not given in the question, we don't know how long this projectile, this cannonball, we don't know how long it's in the air for, and that's what we're going to need to find. So how do we find t? T, first of all, t is the time before the cannonball hits the ground. So t is the time that the cannonball is in the air from the time it's fired until the time it hits the ground. And to do this, we are going to use one-dimensional kinematics. One-dimensional kinematics. Sorry, let me do that neatly. And exclamation marks, because this is exciting. We get to use the tricks that we're well familiar with in 1D kinematics. So what we're doing here is we're trying to find a value of t. And to do that, we need to organize our variables. These steps here will be familiar for many of our previous linear kinematics examples. So organizing our variables, let's look at what we're given and what we need to find. So first of all, we know the acceleration on Earth, negative 9.81 meters per second squared. And we also know delta d, and I want to add a note here. We're doing 1D kinematics in the y direction. In the y direction. So all this here is in the y direction. Because all that matters is this this pointer is going to represent our cannonball. When we're only looking at it in the y direction, it's going to go up some certain height and then come back down and accelerate down towards the earth till it hits the ground. So that's looking at this curve there, but only on the y-axis. So only its up and down motion. So it goes up, slows down, reaches its max height, and then comes down, accelerating until it hits the ground. So when we're doing our 1D kinematics here, the delta dy, that's the distance it travels, or the change in displacement in the y direction. So from the time it's fired to the time it lands, what's the change in displacement? Well, it's this 80 meters. So from the time it's fired, we don't care that it goes up and then down. All we care about is the change from the instant it's fired till the instant we stop the timer when it hits the ground. What's that displacement? So it's negative 80 meters. So negative 80 meters. And we also have a v1y. We have the initial velocity in the y direction, don't we? So this v1, this v1, this vy1, this vy1 here, it's the velocity in the just in the y direction. Remember, we're not looking at the x. We're not looking at this x component, just the y direction. So the velocity in the y direction is 54 sine 30. It's the initial velocity. And I want to do this in pink just so you remember where it's coming from. 54 sine 30. And we type that into our calculator. It's equal to 27 meters per second. So I did this in pink just so you can recall where this value came from and what it represents. And then the variable that is our unknown that we're trying to find, of course, is time. So we're trying to find time so we can plug it back into this formula. All right, so same steps as our familiar 1D kinematics. Next step is to pick an equation. Pick an equation. So based on our variables, acceleration, delta d, v1, and time, I'm going to come over to our chart and pick an equation. So the one that includes the variables v1, delta d, acceleration, and time. So we're going to be using equation 2 here. So because we're using acceleration, delta d, time, and v1, that tells us to use equation 2. I'm going to copy that equation down here. So this is equation 2 that I'm copying down. This is our equation 2 that we're going to use because it contains all the variables we need. On to our next step is to plug in the variables. Actually, plug in values. So we're going to plug in these given values into this equation. Alright. So remember our equation delta d is equal to v1t plus 1/2 at squared. So let's start plugging in these values. So our delta d, negative 80 meters. Negative 80 meters is equal to our v1. Remember, v1, 27 meters per second. 27 meters per second. And our time is our unknown, so I'm going to keep it as a t. Remember, this time we don't know the value, so I'm going to leave it as a t. plus 1/2 times the acceleration, and we should know this one, negative 9.81 meters per second squared. And in case you need to reference that back, it's right here. And multiplied by time squared. Right, so we've got all our variables plugged in, and let's now simplify this. So 80 meters is equal to 27 meters per second times time. It's going to be minus 4.905 t squared. Now the next step here would be to isolate t, but we've got a little bit of an issue here, and that is t comes up with the power of 1 and with the power of 2, so there's no way we can isolate this to solve for t. So t cannot be isolated. And what do we learn from that? Well, that means we have to use the quadratic formula. So when we have t, or some value that can't be isolated, and it has a power of 2, that tells us we're going to use the quadratic formula. So let's start doing that over here. So the quadratic formula. And I'm going to write it out here. T is equal to negative b plus or minus the square root. You should be able to have this memorized by now. It should be familiar from previous years in math class. Just in case, I'm going to write it here so we can reference it. And of course, that is when this quadratic formula holds true, when we have our equation in the form of a t squared plus b times t plus c is equal to 0. So you may have seen this formula with x's, but in this case our variable is t. So it's just that minor change. Same equation. So remember this equation we had here. We need this equation to be written in this standard format so that we can use the quadratic equation. So what I'm going to do here is bring this negative 4.905 to the other side, and this 27 meters per second to the other side. So then our equation will look like this. 5t squared minus 27 meters per second minus 80 meters. And actually I'm going to take out these units because for this part of the solution, the units will only confuse us and get in our way when we're doing the quadratic formula. So for now, we're just going to forget about them. All right. So now you can see we have our equation. This is the same equation as before, but I've brought our 27 over to the other side, so it's become a negative, and our negative 4.905 to the other side, so it's become a positive. And now we have our equation in this standard format with A, B, and C. So now all we have to do is plug A, B, and C into this quadratic equation, this quadratic formula, and we'll be able to solve for t. So t is equal to negative b, so our b is going to be negative 27, so negative of negative 27 is positive 27, plus or minus square root of b, 27 squared. I would write negative 27 squared, but when we square it, the negative will go away, and it'll be a positive regardless. Minus 4, and then our a is 4.905 And our c is negative 80. All over 2 times a, 4.905. All right? Now it's just a matter of typing this all into our calculator. So I'm going to do all this in one go just to save time. And I'd encourage you to type this into your calculator as well, just to make sure you get the same answer as I do. So 27 plus or minus, and all of this, my calculator comes out to 47.94. That is divided by 2 times a was 9.81. Right? And as per usual, when using the quadratic formula, we now have two solutions. So t is equal to 27 plus 47.94 over 9.81. So here our t is equal to 7.64 seconds. And let's do the other one. So t is equal to 27 minus 47.94 over 9.81. And here our t is equal to negative 2.13 seconds. And what do you notice about these two solutions? Well, one's a positive and one's a negative, so they have a positive time and a negative time. And in this instance, a negative time is impossible. We can't have a negative time. So this solution we're going to throw out. It's not applicable in this example. So when we're doing these projectile motion questions and solving for a time, you'll tend to have one positive time and one negative time. And you're always going to want to keep the positive time and throw away your negative time. So we have a positive time and we are going to use that one. And now that we have now solved successfully. We have a value for t. This is what we set out to do. Remember in our first step, we were wondering, what is t? Well, we have this formula, but we didn't know what t was. We have now found the value for t. So we have found from when the ball is launched until the time it hits the ground, the time that it takes is 7.64 seconds. So now we're going to go back to the delta D formula. Delta D formula, that's right where we started. Remember, way back here. So we're going back to here. And I'm going to copy this. Copy. Paste. All right, and now we have values for all these variables. So delta dx is equal to, remember we found the value for Vx, so it's 46.77 meters per second. Remember, that's this one here. And now we have a value for t that we can plug in. So t, which we just found, was 7.64 seconds. 7.64 seconds. So here all we have to do is type this into our calculator. So delta dx is equal to, try to see if you can get the same answer as I did, 357.32 meters. So when we're writing our final answer here, I'm gonna take off the decimals and just round it to 357 meters. Let me make this a nice box. And a little statement to go along with that. A cannonball lands 357 meters away. So this distance here is 357 meters. All right, now let's move on to part B. What height above the ground will our cannonball reach? So this is asking for the max height. This height here, that's its maximum height. What height above the ground is this? So we have this max height. What height above the ground? So what is this height? Again, this is going to be a 1D kinematics question. So 1D, one-dimensional kinematics. So first, let's find our variables. So variables. Here. It's going to be tight for space, so I just want to put that up there. Do this in green. So our V1y this is pink. So pink. So we're looking to find the maximum height. We know that the initial velocity is 54 sine 30. So our V1y is equal to, again, I want to do this in pink so that when you're looking at this, you can recall where the value came from. And when we plug that in, we get 27 meters per second. And this is the same value as we had over here. And another piece of information we have when we're trying to find the maximum height. When we're trying to find the maximum height, we know that is when this cannonball, it has an initial velocity in the y direction, but then it slows down, and at its max height, the velocity in the y direction is 0 meters per second. So V2y, 0 meters per second. Our acceleration, as always, on Earth, negative 9.81 meters per second squared. And then the height that it reaches is our unknown. So our next step, once we have our 4 variables organized, to pick an equation. All right, so let's pick an equation. We have V1, V2, acceleration, and delta D. So V1, V2, delta D, and acceleration. We're going to use this equation here, equation 5. So, because we have V1, V2, acceleration, delta D, that tells us to use equation number 5. I'm going to write that down here. So V2 squared plus V1 squared. V2 squared is equal to V1 squared plus 2a delta D. Again, this is just another linear kinematics problem, so these steps should be familiar. So we're going to plug in our values now to the equation. So remember the equation. V2 squared is equal to V1 squared plus 2a delta D. Now let's plug in our variables. So V2, 0 meters per second. So V2 is 0 meters per second. We're going to square that, even though it doesn't matter. It's equal to V1, 27 meters per second. V1 squared, 27 meters per second, plus 2 times the acceleration, negative 9.81 meters per second squared, negative 9.81 meters per second squared. So I'm getting a little tight there. And delta D is our unknown delta D. So change in displacement. And let's just clean up this formula. I'm going to plug this into our calculator. 792 meters squared per second squared plus, rather minus, because we're multiplying these two, 19.62 meters per second squared multiplied by delta D. All right, and now it's time to isolate the unknown. Just to isolate the unknown, what we're going to do is, continuing on with this equation, we need to isolate our delta D to its own side of the equal sign. So the first step to do that is bring the term that includes the delta D to the other side of the equal sign. So since it's a negative, it's going to become a positive on this side. So you're going to see this here is a positive is equal to 729 meters squared per second squared. You can see how this equation is the same as this equation. And now isolating for D, we're going to bring this onto the other side as a division. 19.62 meters per second squared. And I want to know if we can make a little bit more room here. So here we have that our delta D, found a value for it. Plugging this into our calculator, 37.16 meters. So this value that we've just found, now what does that represent? Well, that represents this distance here. So the max height relative, this is the max height, but relative to the point which the motion started at. So from the time, or from the height that the cannon was fired, from that point it goes up 37.16 meters. So there's one more thing we have to do before this question is done, and that is to add the height of the tower. So add the height of the tower. So remember, we found one value. We found 37.16. That's this here. But the question's asking us, what height above the ground will it reach? So when we're looking at the height above the ground, we need to add this 80 meters. So we need to add this, it's 80 meters. So that's going to be a relatively easy step. Just a simple addition we have to do. So it's going to be 37.16 meters. Remember, that's the max height. The max height above where it was launched. And then 80 meters is the height of the tower. And all we do is add these up to get 117.16 meters, telling us that the height, let me round that, the height is 117 meters above ground. above the ground. So as a final statement, the cannonball reaches up to 117 meters above the ground. All right, so that's part B. Now let's move on to part C. With what velocity, so it's a magnitude and direction, will the cannonball hit the ground? So we're looking for a final velocity. So we have a formula for the final velocity given the values that we have. So a reminder of those values we have: v1y, 27 meters per second, acceleration negative 9.81 meters per second squared, and the delta d is going to be negative 80 meters. Right? And then we want to know our v2y. So remember, with what velocity will the cannonball hit the ground? We've got our v1 in the y direction is up, and then it has a certain acceleration downward, and the distance traveled from the time it was released, or from the height it was released to the height that it hits the ground at, the displacement is negative 80 meters. So that's where these values came from. And then based on that, so here's our variables. Now let's pick an equation. So v1, acceleration, delta d, and v2. That tells us that we're going to use these variables, this equation number 5. And I'm just moving a little quicker through this because it's very similar to what we've done in the last few parts. So because, well, I'm just going to write here, therefore use equation 5. That is v2y squared is equal to v1y squared minus 2a delta d. All right, and now start plugging in variables, plug in values. So our formula, v2y squared is equal to v1y squared minus 2a delta d. Sorry, I wrote that one wrong here. This should be a plus. Just plus 2a delta d. So let's plug in these values. So our v2y, that is our unknown, is equal to v1y, so that's 27 meters per second squared, plus 2 times our acceleration, negative 9.81 meters per second squared, times delta d, negative 80 meters. It's delta d, negative 80 meters. And what I'm going to do here is bring this squared to the other side. So the opposite of squaring something is going to be square root. So what you're going to see is v2y is equal to the square root of all this. So the square root, 27 meters per second squared, plus 2 times negative 9.81 meters per second squared, minus 80 meters. And that will give us for V2y, plug this into our calculator, try this along with me and make sure you get the same answer. It's always good practice to use your calculator even when you're watching these example problems. It's really good practice to just follow along with. So here we have a value of 47.94 meters per second. All right, so we have our final velocity y. So this is the speed in the y direction that our cannonball is traveling. So straight down. This is our y direction down that the cannonball is traveling with as it hits the ground. So let me draw out a little diagram here. Now that we have some values. So in our y direction, we have a speed of 47.94 meters per second. And we also have, so that's our y component, we also have an x component. Remember the speed in the x direction, that remains constant throughout the entire flight of the object. So it never slows down or speeds up in the x direction because we're ignoring air resistance. So it's going to, like this Vx is going to be the same throughout the entire time. So just as it lands, it has the same Vx as it did when it was launched. So this 54 cos 30 is going to be our final Vx as well. And if you remember our value which we calculated for our Vx was 46.77 meters. And we can remember that here where we calculated it. That's this value here. So adding these vectors together, we get a resultant vector. Get this resultant vector. This is our resultant. With value r, this is the magnitude r, we don't know it. And when we're asked to find the direction, we're going to establish the direction as below the horizontal. So I'm going to do this in another color. This is horizontal. And we want to find the angle theta. All right, so let's start. We're going to need to find the magnitude and the angle. Let's do one at a time. We can start with the magnitude. As you can see, because this is a 90-degree angle, we can use the Pythagorean Theorem, and that tells us that r squared is equal to 47.94 squared. I'm going to add the units actually, plus 46.77 meters per second squared. So the hypotenuse squared, this is the Pythagorean Theorem, the hypotenuse squared is equal to the other two side lengths squared and added together. So let's write that out. Isolating for r, so we're taking this squared and bringing it to the other side as a square root. It's 46.77 meters per second squared. And that will give us our value for r. So again, try this in your own calculators. I got a value of 66.98 meters per second. So we have a magnitude. We have a magnitude, 66.98 meters per second. And now we're going to find the angle. And how are we going to do that? Well, we have this angle that we want to know, and this triangle that's related to it. But this angle is not inside the triangle. But if you notice, we know our Z pattern, and we have this kind of a Z here. This is a Z. This is our Z pattern. So if we know this angle, this angle, and this angle are the same. So if this is theta, this is also theta. That's our Z equivalent angles in the Z shape. So the equivalent angles using the Z shape. So I'm going to write this. This is also theta. These are going to be the same angles here and here. So now we have an angle inside the triangle, and we know the side lengths. And you can pick whatever side lengths you want to use. We're going to be doing SOHCAHTOA. So SOHCAHTOA. And in this case, I'm choosing to use, from our angle, the adjacent side and the opposite side. So the adjacent and the opposite, that tells us we're going to use tan. So tan theta is equal to opposite over the adjacent. So that means that theta is equal to the tan inverse of the opposite over the adjacent. And I'm going to plug in those values now. So from theta, the opposite is 47.94, and the adjacent is 46.77. So let's plug those in, 47.94 over the adjacent, 46.77. And when you plug this into your calculator, make sure you're in degree mode. That'll be important for your tests as well. Get a value of 45.7 degrees. And that is below the horizontal. So we have our resultant vector, the magnitude, and the angle. Let's just write this out in a final closing statement. So therefore, the cannonball hits the ground, with a velocity of, I'm going to round our magnitude to 67, so 67 meters per second. And the angle, I'm going to write here, I'm going to round it to 46 degrees below the horizontal. So that is our magnitude and our angle. And I just want to show you this on this graph. So we're looking at this point here where it hits the ground. This is our resultant, and our x component and our y component. And these are all values. These are all the values that you see here. And of course the angle. The angle, of course, of theta. And that is a solution to this problem.